Mi dite voi quando posso iniziare, vero? Posso iniziare? So welcome to the second lecture of this course. Today I will derive together with you the formulae that are describing two types of acceleration that occurs on charged particles in the galaxy in the magnetic field. These are two types of acceleration called first order and second order. I will start from second order Fermi acceleration because it was, well, historically the derivation given by Enrico Fermi, and also because with a slight conceptual modification we can go more easily to the first order Fermi acceleration. So you can find, as I was hinting at you yesterday, the basics of this theory in a paper by Enrico Fermi dated back 1949. So the fundamental idea is that a charged particle scatters on magnetic mirror. A magnetic mirror is a definition for a rigid target. So we have this mirror, which is called mirror, because this effect makes the hypothesis that an incoming particle, so our charged particles that are wandering in the galaxy, encounters as a matter of fact, a turbulence in the magnetic field, but the interaction is that the particle arrives and is scattered back and doesn't go to this side of the mirror. So it is a rigid scattering. The particle doesn't cross let's say, this effectively magnetic turbulence, which propagates, that moves in the galaxy with the speed that we have seen yesterday, and which is the Alphen speed. So the velocity at which these Alphen waves, these irregularities in the magnetic field, move in the galaxy. So we have this target, a particle which makes an angle theta with the normal to the scatter, and this particle, just to keep the notations and not to confuse them, is arriving in its motion on the irregularities of the magnetic field. This is a head-on collision. And similarly, we can have particles that hit the turbulence, that hit this magnetic mirror on the other side. So again, the mirror is moving in this direction with Alphen speed, and a particle can arrive in this direction, so in the back, on the back of the target. The particle scatters, and it is reflected in this way. And similarly happens for the scatters that occurs tail-on instead of head-on. This is a tail-on collision. This is the x-axis. I will deal with a one-dimension problem here, but you can easily generalize to three-dimension situation. So M is the mirror or the magnetic surface that makes this scattering possible. V is the speed of the particle, and VA is the speed of M, and it is the Alphen velocity. Let's make the hypothesis, which is very reasonable, that the mass of the scatter of this M is much bigger than the mass of the particle, which is a proton, which is an electron. So that makes sense. So the recoil of M is totally negligible. We only consider the recoil of the particle. So let's put in the center, in the frame of the cloud. So in the center of momentum of M of the cloud. So the particle has E as an energy, P as a momentum, V as its speed. In the mirror frame, so in the frame of M, the particle has an energy E prime, which is given by the Lorentz factor gamma A, so which takes into account the movement of the mirror with respect to the particle, E plus, and then we have VA, P cos theta, because it is in the direction of X, in the direction in which the mirror is moving. And gamma A is 1 over 1 minus, and it is the beta. Let's write via over c squared. So the problem is relativistic because the particle is relativistic. The momentum in the x component, which is p prime cos theta prime, is given by gamma A, and then we have p cos theta plus VA c squared E. So now it is the point. The point is that when the particle collides with this magnetic wall, it is reflected. So what was p prime x changes into minus p prime x. Indeed, the momentum changes its sign, but the energy is conserved. So these are the 2 points that are crucial in this derivation. So now we transform again the energy that is of the particle after the reflection in the observer frame. And now I write E second, so the energy in the observer reference frame after this scattering. So since we are transforming back, but P has changed its sign, now we have the Lorentz factor E prime plus VA P prime. Okay, it was already empty, sorry. So now we elaborate a bit on the energy of the particle after the reflection in the observer frame. So it is, I have written gamma A. Instead of E prime, I write the above expression. So let me just put this way. So we have gamma A, E plus Alven velocity, P cos theta, and this is for E prime. And then I have VA. And I have P prime X. And I copy just this expression that we derived before. So we copy P prime X, which is gamma A, P cos theta, plus VA over C squared X, E. So we do a little bit of algebra, and this is gamma A squared in front of everything. And then we have E plus VA P cos theta plus VA P cos theta plus VA over C squared times the energy. This is gamma A squared, energy, 1 plus, this is twice the same quantity, so twice VA, P over E, we have cos theta plus VA over C squared. We can write just using the kinematics relation. So gamma A squared, 1 plus twice VA, V over C squared. So V is the speed of the particle. And then we have cos theta plus VA C everything squared. So this is just a little bit of algebra for the quantity that describes the energy of the particle after the scattering on the magnetic mirror. Now, the idea is to make an expansion on VA, because I discussed at least once, VA is small. It is of the order of kilometers per second or few tenths of kilometers per second. So VA over C, you see here there is a VA over C term, can be considered a small term. And the expansion is getting E second equal to 1. I just rewrite VA squared, I rewrite gamma squared. 1 plus twice VA over C, V over C cos theta, plus VA over C squared. There was somewhere the energy. Good. And now we do the expansion here. If you do this, you have E, 1 plus VA squared over C squared. And the rest isn't changed at the moment. And at this point, we do the calculation, and we have E. So this is 1 plus 2 VA over C, V over C cos theta, plus VA over C squared. And then we have VAC squared. We only take the first term because we stop ourselves at second order in VA. So it is plus VA over C squared. So we can compute E second minus E. So everything is in the observer's reference frame. And this is the difference in energy that this particle has experienced when scattering off the magnetic mirror. So this delta E is easily found in this expression. So it is twice VA over C, V over C cos theta, plus twice, VA over C squared. Well, now we have to do one other step in this computation, because you see it is done only for one specific angle of incoming particle with respect to the direction of the mirror. So we have to average on all the possible angles that the particle has arriving and scattering. So we have to average cos theta on its probability to occur. So now I don't demonstrate this, but you can find in many books that treat relativistic particle scatterings that the probability that a particle scatters with this velocity and with this angle is proportional to the Lorentz factor 1 plus the speed of the scatter cosinus theta. So this is, how to say, I let it at your derivation, or maybe you have seen it when doing some Compton scattering. Or therefore, we have to average the function here that depends on theta, on the probability that we have defined here. And so I'm going to do this calculation. So the probability has, of course, only to be average with this part. The rest is not dependent on theta. So we compute 2 times VA over C cos theta, and this is twice VA over C, and the average is the integral between -1 and +1 cos theta, which is from the function, and then we take the term of the probability, which is 1 plus VA over C cos theta, d cos theta. And we normalized to the total of the probability between -1 and +1 of this probability, 1 plus VA over C cos theta d cos theta. All the other factors cancel, and we can also consider that V over C, since the particle is relativistic, is close to 1. So we do this simple integral, which is 2VA over C, and then we have the integral of these two power functions. So it is 1/2, let's say, x squared plus VR over c, 1/3 x cube, taken from -1 and +1. And here we have x plus VA over c, 1/2 x squared taken between +1 and -1. And this is easily done and gives you 2/3 VA squared over c squared. And it is right this average over all the pitch angles that gives us a term which is only proportional to VA squared, let's say over c squared, VA squared. Now I write the full expression for the delta E term. So we are left, we are here, okay? So we are considering the average of this quantity, the average of the difference. We can therefore good. Okay, so let me see. Yes. Now we can write the difference, the average of this quantity normalized to E. There was a V over C, which is, of course, and then you can put it at the denominator. And you have 2/3, which is the last result. And then don't forget that we still have, there was a E that I forgot here. Everything was E minus E. I think I forgot to put this proportion to the energy. Anyway, computations should not be difficult to check. The more difficult things were the ideas of the scattering and of the energy. So we have the first term, the average over cos theta, and then we are still left with plus VA over c squared. That gives us this important result that the average relative energy gain is a coefficient, specifically A30, but what is very important is that this term is proportional to VA squared. This is the second order Fermi acceleration. These kind of scatterings have the same result both for tail-on and head-on scatterings. So anytime a particle scatters on a magnetic mirror in this direction or in that direction, the particle always gains energy. because there is always this term VA square. There is no longer any dependence on the sign between the direction of the particle and the mirror. So this is a process that is a second order, so it is not very effective because, again, VA over C is small. The gain in energy occurs, but it is not a big gain in energy. In fact, the second order Fermi acceleration cannot explain in this formalism why particles are measured at very, very high energy. It cannot be this second order process. Nevertheless, this second order process, I will show you the consequences of this in the equation that rules the transport of a particle, enters in the propagation of cosmic rays and is important at some energies. So the reason why this acceleration is not very effective is, of course, because of the speed, the alpha speed, which is because of these mirrors, these scatterers are pretty far from each other. An average distance in the galaxy for this turbulent grains, these turbulent inhomogeneities, is a scale of about 1 parsec, which is huge with respect to the diffusion of a particle. So it cannot be this efficient. And then there is also another aspect that I will treat in some other context in my next lecture, which is that these particles very often, depending on the particles, also lose energy. So there is a process that makes the particles gain energy and others that makes the particles lose energy. So let me just derive qualitatively also the expression for the typical gain of energy, not with respect to the energy itself, but to the time, which is important when we write the diffusion equation. So what I want to estimate is the gain in a certain time integral, or let me write the differential expression for it. And to this aim, we have to take into account that in some delta t, the particle, which is going practically to the speed of light, travels a distance which is L divided cosinus theta. So L is the straight distance between two mirrors. The particles, maybe it's better if I do it. So we have one mirror here, we have another mirror here. The distance is L between the two, and the particle has some angle for going to one over the other. So the distance traveled is this L cosinus divided by cosinus theta, and the typical energy gain, the rate of energy gain, is a third VA over C squared, and this time we have to multiply by E because we are computing with respect to the time, 1 divided 2L over C. In this expression, I made the average on the probability that cosinus theta occurs. So there is again an angular average which is done. It is kind of this computation here, okay? That gives globally a factor of 2. You can compute yourself this. It is nothing different than what I have done so far. So, in addition to this very relevant result, so delta E over E, we can also compute the energy, we can even predict the energy gain as a function of time. And this is a function of energy, where alpha is this coefficient that I have derived here, which is 4/3 VA over C squared 1 CL. If one, of course, knows VA and L, which are properties of the magnetic environment. So now let's try to understand why this mechanism, while being, of course, very well motivated, doesn't explain existence of very, very high particles. Very, very high means hundreds of GeV and even hundreds of TeV. So some other scientists took the idea of Enrico Fermi about this second order acceleration process, but they make a very crucial hypothesis different from the one of Fermi. That means the particles, well, there are some, let me rewind, there are some astrophysics environments in which particles are not scattered, are not reflected, but can cross this environment. We know that these environments can be the front shocks, for example, of supernova remnants, which so far are believed to be the main accelerators of particles in the galaxy. So anytime a supernova dies, it collapses, and then it undergoes a strong shock. This shock propagates at a significant speed in the galaxy and can be the origin of an acceleration process for a charged particles. And now we see what is this mechanism. And this mechanism is called first order Fermi acceleration. So the idea is that there is, again, a strong magnetic environment, but this time the particles can cross this front shock in the specific case. So I will do some scheme in order to get us a bit more acquainted with this theory. First of all, let's consider a charged particles, for example, electrons or protons that are in the interstellar medium, and they have a Larmor radius, which is mv. Charge, I put the modulus because, of course, it can be for electrons or for protons, times the magnetic field. We have this shock. The shock has a thickness, and the Larmor radius must be much, much bigger than the thickness of the shock, which is the case usually for particles encountering the front shock of an expanding supernova remnant. So this is one of the hypotheses, that we can consider the front shock as infinitely thin with respect to the Larmor radius of the particle. So now I try to depict the situation in 4 different reference frames. So we try to understand what is happening. So this is the front shock. The front shock is moving in the interstellar medium in the direction that I put here with a speed that I call u. This region here is called upstream, and the region that goes down to the center of the supernova remnant is called the downstream region. So here, in other words, we have the interstellar medium particles that are in the interstellar medium at some speed. And the upstream region counts particles with some density, with some 1, some speed v1, some temperature. We won't deal with thermodynamics here, but the equations that rules this situation are finally gases equation. This is the shocked region. And here we have ρ2, T2, and V2. This is in the observer's frame. You observe this situation and you see the 2 environments with their proper speed, and you see also that the shock is moving at some velocity u. Let me still add some consideration that are not relevant today for our computations, but if you deal with all the equations, it is important, namely that this shock moves at a speed which is much bigger of the sound speed in that medium. And depending on the supernova, there are different classes of supernova remnants. This speed is at least 10 to the 4 kilometers per second. It can be very high. Now, let's consider another frame in which the shock is at rest. So, this frame is for the shock at rest. So if the shock has speed equal to 0, well, we know that in our frame, we are the observers, it moves at u. That means that this is the upstream again, and this is the downstream situation. So here we have the interstellar medium particle, and these particles have a speed which is this way. So they encounter the shock which is coming against them. So the modulus of the speed is the speed of the mirror, just the sign, of course, is different. And they have their ρ1. This is V2, again, T2, and this is ρ2. So the shock here is at rest. So in this case, the upstream gas, the upstream particles, flow through the mirror, not the mirror, sorry, through the shock with this speed. And when they leave the front shock, they go into this part, into the downstream region, in which all the particles have a speed which is v2. And they in fact isotropize their speed to v2. But let me just say that the continuity equation tells us that this is the case. If the strong is very strong, we have that ρ2 divided ρ1 is equal to gamma plus 1, gamma minus 1, where gamma is the ratio of the specific heats of the gas. Cp is the specific heat at constant pressure, and Cv is the specific heat at constant volume. And looking back at some thermodynamics, which I don't recall here, in our case, gamma, if the gas is monoatomic or if the gas is fully ionized, this ratio of specific heat is 5/3. Therefore, the ratio between ρ2 and ρ1 is 8/3 divided 2/3, that is 4. And we have that V2 is, in this specific frame, 1/4 of V1. This is just to make some exercises, but what is more relevant to our case are the two following reference frames, which are more interesting, and we will start from that. So now we put in the reference frame, we have our shock here, we have downstream, we have upstream particles, and we put in the reference in which the upstream particles are at rest. Okay? So, in this case, if they are at rest, they have V1 equal to 0. These are the particles that indeed are at V2, and you can derive from the reasonings that I have done before that V2 is proportional to U. So in this frame, it is the shock that moves into the upstream gas, into the upstream interstellar medium. So in this case, the interstellar medium is stationary, but the front shock moves. Since it moves, with the time going, there are particles that were at rest that are crossed by the front. So the particles in this frame goes from a system in which everybody is at rest to a system in which there is a sea of particles, all with velocity v2. This crossing, I will show later on, this is just for a bit of visualization, we will use the formula just in a while, so we will derive. But this crossing implies that the particles that are hit by the front view, the front shock, have a little gain of energy. And I'm going to compute this. So particles diffuse from upstream to downstream, from being at rest to have a little velocity because they are absorbed, they are crossing this region. Maybe I can also draw here. Now you have learned the situation. We have the other way, which is the downstream particles which are at rest. So in this case, the particle in this part behind the shock are stationary. So the speed is equal to 0 in that frame. So just sit, imagine to be sit on a particle here. Okay, you are sit there, you don't move, the particle doesn't move, but the speed, the front shock moves. The front shock moves, and they see particles from V1 going towards them. So in this case, the particle velocity distribution is isotropic behind the shock, and when the particles cross the shock, they encounter upstream particles. This is again the same movie. That comes towards, of course, the front shock as before. And as in the previous case, also in this case, the particles that cross the shock from the other direction gain some energy that I call delta E. So now I'm going to compute this increase of energy. But keep in mind that this is really the main physics of the acceleration process of this first order. We will derive in a while that it is first order. The idea is at any crossing from one direction to the other and the opposite, at any time it occurs, the particle gains a little or big some amount of energy. So it is each crossing that gets the particle increase its energy. So now let's try to derive the energy gain. We can put, for example, in this reference frame here. So when the particle crosses the front shock, it has an energy E prime, which is gamma. I put an underscore V, which is the speed of the particle, because now the frame is shifted not by the speed of the front shock, but by the speed of the particle. Nevertheless, the speed of the particles is linked to the speed of the shock. So we have, again, this transformation when the particle makes one crossing in the reference frame that I marked here as a star. Considering, of course, that the shock, as just the example I made before for the second order, the shock is moving in the x direction. So it is a 1D, and I put the system in the reference in which x is the direction of the shock, of course. So E prime is the particle's energy when it passes to the other region. So if the shock is non-relativistic, gamma V is equal to 1. But particles are relativistic. So E prime is, with a good approximation, equal to E plus PXV, to say PC plus EC V cos theta. So we have that the energy shift is E prime minus E, and it is equal to E over C V cos theta. So again, we have to consider to average over this angle. And again, this is a bit different as before, because before it was a rigid scattering. This is a bit different situation. We have to consider the probability that a particle arrives at an angle which is comprised between theta and theta plus the theta. And we should also consider the rate at which it arrives at the shock. So again, I will skip the derivation of this probability. You can find it in kinetic theories. So let me write that this probability is a normalization factor. Maybe I can write a bit more consistently. P theta, the theta, so the probability that it arrives at a certain angle and at a specific rate, it is given by this function. So if we give this for granted, or you will derive for your exercise, we can first of all fix the normalization factor. And the normalization factor is found this way. We normalize to 1 the probability, and the probability is between 0 and 90 degrees to cover half of a sphere. And this is A sin theta, cos theta, d theta. And you can find that this number is 1/2 A. So the normalization is equal to 2. So maybe I go directly here. And now I want to compute the average energy gain, averaging over the angle. So the average is dE over E, just look some rows before, and this is the integral on the cosinus of theta between 0, well, we can put, okay, V over C, cos theta, I write P theta d theta, okay? So maybe this way is more clear, so 0, 90, V over C, twice, and then we have cos theta, sin theta, and another cos theta over the theta. And this is an easy integral to perform, which is twice V over C, and it is minus 1/3. You have a minus for the derivative. Cosinus cube theta, where you take the angle between 0 and 90. And this gives globally 2/3 V over C. So this is the algebra. The physics is that the average relative gain is proportional to V over C. This happens at one crossing of the shock. The other way round, the numbers, the signs are the same, because it is just everything vice versa. That means that a full tour of the particle crossing twice the front shock makes the particle gaining twice this quantity. So for a complete crossing of the front shock, our proton or our electron, if nothing else happens, gain 4/3 V over C in energy. This is the fractional gain, and this is why it is called first order. Yes?
Why do we gain a factor 2? Because I was wondering if we expect only that once the shock passes, we just gain 1.
Yes, usually, this is, you agree with me that if the particle makes one and twice?
Yes.
Okay, so this is algebra. What happens in the reality is that one has this shock is moving, and the particles around the shock experience a kind of diffusive acceleration, which is something that I didn't want to present in these lectures because it is pretty complicated, but yes, the question is very interesting. The particle around the shock makes kind of this. You should see these lines as moving in time, of course. So while the shock is moving, the particles are supposed to go back and forth across the shock. And indeed, to answer to your question, this is not the whole story. So this is to show that at each crossing, the acceleration is first order. But then, to fully explain what we observed, that namely these particles not only accelerate in a diffusive way, but also at some point can exit the front shock, because otherwise they would stay confined forever. One should write an equation, a diffusion equation for particles diffusing, and let's say in these shock environments. So, I mean, I prepare just some notes, but it is probably a bit complicated. I mean, not complicated, but since we have some limited time, maybe I put these notes in my online material, and you can have some hints that starting from a transport equation for the transport equation is this one. I can write it. It is x, of course, is the coordinate around the shock. There is a diffusion coefficient for this shock environment, which is in principle not the same as the galaxy, in principle. And then we have this way, we have the velocity, which gets some convection. And then we have 1/3 du over dx, p, df over p. This is the compression terms. And then we have a source term, function of x, p, and t. So this is the equation that one starts from. It is, of course, far from trivial to solve it. There are several groups, not several, few groups that try to solve it numerically with simulations of particles around the cross shock. What is interesting is that the spectrum, which is called here half of this particle, treated in this way, assuming that this is the source and that the acceleration is, as I just explained you, permits to arrive to a prediction which is a power law in energy. Okay, so you can find in some lectures or books devoted to acceleration, but this is very important, that starting from first order Fermi acceleration with a transport equation in the shocked region and taking care of nonlinear effects, one can arrive at a spectrum acceleration spectrum, which is n is connected to f, which is proportional to p 2 plus r minus 1 minus r, the p dove, when this coefficient is usually 4. If it is 4, you have 2 plus 4, which is 6, divided by 3. So if it is 4, that gives us p squared over the p. So these are just very quick hints, but if somebody is interested, I can also give you some more references when you can find all the equations and arrive to this consequence. So this theory predicts that particles that are accelerated across the front shock and undergoes first order Fermi acceleration can have a power spectrum of injection of accelerated particle from the shock in the galaxy, which is close to a power law to 2. So, take into account what we have seen yesterday and what we have seen today, we can so far saying that particles, charged particles in the galaxy, first of all, have a diffusion in space, that's what we have seen yesterday, can be accelerated up to high energies, and can have an energy gain of some kind thanks to the second order acceleration process. Now, these are some, let's say, at least a few of the main ingredients that rule the transport of the particle in the galaxy. Now, what I will do now is to write the full transport equation, some of the pieces being the ones we have dealt now. And after this, I will describe piece by piece this lecture and the other one. And the transport equation that I'm going to write now, we will use it in the next lectures. And it will also used by Francesca Calore this afternoon in the exercises that she will propose you. So you will start with her, with this equation, and you will see with her in some specific situation. So the structure of the equation should already be clear to you because of the work that we have done yesterday from the fixed and the continuity equations and from these transport equations that we have discussed, acceleration processes that we have discussed so far. So now we see the transport equation for cosmic rays. I will write briefly n, but this is the same quantity that we have seen yesterday. The density function of a particle, which is a function of energy, position, maybe I call it R, and time. In principle, the system could be not stationary, so we leave a derivative of a time indicated. Then we have the diffusion in space, which is the nabla times a diffusion coefficient. So now I don't remember if yesterday I called it D or K. It will probably be a bit I will use K or D. These are indeed the two letters used in the literature. So if you will deal with this physics, you will find both K and D. And so you are already ready. This is the diffusion coefficient, or in principle, of course, it is dependent on energy, and I showed you yesterday this, and also in space. Then we have a term that I will hint at it tomorrow, which is a convection term in the galaxy. And this is linked to space, only space derivative. And now we have to consider that these particles undergo gains and losses in energy. So we have coupled energy differential equation with, yes, sorry, the? Yes, there must be two nabla here, yes. I forgot, sorry. Yeah, thank you. Yeah. There is a nabla here. Okay? Yeah, thank you. It's a second order, it was not, thank you. And this is the term with the energy gain, which I will detail in the next lecture. And then we have minus C, or the signs, of course, depend. One can have a minus here, and a plus here, and minus here, so just... and this is dN over the E. And this is the part of the differential equation that takes into account energy changes. Then we have two terms which deal with nuclear physics. Just now look at them, and we will work on them a little bit tomorrow. So we have a particle that diffuses in space, that probably undergoes some convection, that can lose and gain energies, that can have some nuclear physics reaction, of course, when encountering other particles. Microphysics is always there. And now we write a generic source term, which I write as QER, which can be of different origins. One origin is the one that we have seen today, that is acceleration across the shock waves. There are also other sources, and this will be discussed in the following. So, the spectrum of cosmic ray can in principle be time-dependent. This depends, the fact of considering this equation stationary or time-dependent depends on the specific case you are dealing. For example, if you consider protons in the whole galaxy, protons are pretty stable particles. They don't break themselves almost. And the equation for protons and many nuclei can be considered as stationary. And the average quantities that we compute are very representative of the functions of the spectrum of the particles. For example, this is not longer true if we consider particles, for example, produced by sources which are near the galaxy and sources that are alive for some time and then decreases their acceleration power. This, for example, is true for pulsars, and this is a topic that you will partially see today, and I will describe also a bit tomorrow. And then there is the second term, which is the spatial transport, that it is due to the inhomogeneities on the magnetic field, to some convective wind. If I have time, I will give you some hint about this. Energy losses and gains, as I told you, are here and are very different depending on the species. The energy losses which are described in this very generic term B, are very violent for electrons and positrons, so for leptons that are very light, and they undergo violent radiative cooling. And tomorrow I will tell you the basics of this. This term here, you see it has the same sign, of course, the same sign, but there is equal, so it is a term which is opposite to the source, so we can create cosmic rays, but then these cosmic rays can destruct themselves through inelastic interaction of the interstellar medium, or if nature creates some, for example, beta radioactive nucleus, it can disappear by decay. The sources of cosmic ray are described by this term Q, and in the physics of cosmic ray in particular, in galactic cosmic ray physics, we define two classes of sources. One are the primary sources, and the other one are the secondary sources. Primary sources are all the species that are produced and accelerated directly in the accelerators in the source sites. So all the primary species are the ones who are, for example, accelerated by supernova remnant. Supernova remnants are primary sources of cosmic rays, or a primary proton is a proton that has been accelerated in supernova remnants. Another class of primary sources are pulsars. I will deal a little bit later on, and you will also see this afternoon. Supernova remnants accelerate nuclei, so proton, helium, carbon, partially nitrogen, oxygen, and iron. These are the main primary nuclei. That means these are nuclei that are already in the supernova environment. And usually these are particles, proton and helium, that are relics from the Big Bang. And the other nuclei are produced by supernova explosions, by the thermonuclear collapse of supernovae, by the fusion and then the collapse. Pulsars have a very different mechanism. This supernova remnant, I forgot to say that since the interstellar medium is crowded also by electrons, they also accelerate electrons. The acceleration process is in principle the same, but electrons also, when they are accelerated, have a dramatic energy cooling, so it is impossible to treat only the acceleration without considering the fact that they lose a lot of energies. Pulsars are in particular accelerating electrons and positrons. These two particles, E plus, E minus, are produced in pair by photoconversion in the strong magnetic field of the pulsars. We have also another, this time hypothetical, source of cosmic rays that I deal with in the next lectures, which is dark matter in the galaxy. And for the moment, I don't say anything more than that. secondary particles are those particles which are not present in these sources environments, but they are produced by cosmic ray physicists say spallation reactions. Spallation comes from Latin shoulder. I don't know the very historical reason, but in Italian we can better understand the how to say, violent process. That to say, one nucleus, one, iron or carbon or whatever, if interacts with the interstellar medium, and the interstellar medium is made mainly by hydrogen and helium, can break itself by totally inelastic reactions. This is what you better learned in your classes at the university. But cosmic ray physics say that the birth of this other nucleus, and two, is by spallation. For example, you can have here a carbon that kinks of a hydrogen, which is proton on the interstellar medium, and it produces lithium plus anything. This is a possible reaction. So I will show you tomorrow that, because now I don't want to open my PC tomorrow, I will install you to show you some pictures that there are nuclei such as protons, helium, the ones that I wrote before, that are practically fully primaries, and other that are fully secondaries, and other that are mixed. And the fact that they are fully primary or fully secondary is interesting for the propagation history. So now, in the aim of explaining a bit in more detail this pieces of the diffusion equation, I want to spend a little bit of time on this term here. Since today we have studied the second order Fermi acceleration, I would like to connect this energy gain term with this shape in the equation. So the second order Fermi acceleration is an effect that implies energy gain on cosmic rays, and it is called reacceleration. So let's make the hypothesis that we have a particle which can gain a momentum. This particle has a position and has a time. It's on time, of course. So this particle has a distribution function f, which makes the hypothesis that it has reached the value p for its momentum in a time interval x, in a space interval x plus delta x, and in a time interval t plus delta t. This distribution function is linked this way. Let me write and then explain. It is the integral over this momentum change, this little momentum change, delta p, times a function psi, which is p minus delta p, times f, p minus delta p, x, and t. So let me explain what I have written on the blackboard. Let's make the hypothesis, because now I want to study the equations that rule energy change. Okay, so this is the aim of this discussion. We have a distribution function that describes a particle that has gained delta p. So the particle was at p minus delta p, and it went to p. I'm using the same formalism as this paper written by Roger Blandford and Eichler some years ago in 1987. So it is the big paper, and there is also a part on this energy change. So the hypothesis is that if a particle undergoes an energy change of delta p, this energy change only depends on the change in space x plus delta x and t plus delta t, and not all the past history. It is a kind of Markov process. So the process depends only on the closed situation in phase space. This function psi is the probability function that describes that is the probability that a particle with p minus delta p goes to p by delta p changing in momentum. So now I don't want to do all the steps, but only to tell you that if you Taylor expand the first and the second member of this equation, and you consider that this psi is normalized, one can obtain a very famous equation. So my idea was just to give you some hints to derive this equation, which is called, I'm going to write it is the Fokker-Planck Equation, which is useful not only for diffusion in momentum, but maybe if I hope that you will stay in physics forever, but people who now predict some economics processes can sometimes also encounter this kind of equation, which are second-order differential equation for changes of quantities that are class of Markov processes. So if one expands in Taylor series and considers this normalization here, obtain this Fokker-Planck equation. It was one of my aim just to show you so that you can see at least once, which is, again, the possibility that the process is non-stationary, which is the f over dt, and then there is a kind of, let's say, modification in space with the velocity v, but then there is this equal to, there is this part which is the energy dependent part, and it is the derivative over p minus the average over dp on dp over dt times f plus 1/2 that comes from Taylor expansion d over dp delta p over delta t averaged f. So the derivative is for all this. Let me check. Okay, plus. No, I already put this parenthesis here, so this is correct. And this is closed. I erased. Okay. Now, I have put these numbers, this coefficient, delta P over delta T. They can be derived by the expansion if you do it properly. And I only write it for this one. Delta P over dt average is 1 over delta T, and it is the integral of d delta P. The distribution function, the probability, psi P delta P, delta P. I don't write the rest. You can go to the reference by Blandford. No, maybe I leave it here. And again, a similar expression is for delta P, delta P. Now, there is another step, then again, I just cite to you, and you can derive yourself if you want, is that if the recoil of the scatter can be neglected, as I told you before, these mirrors are, of course, enormous with respect to the particle, so there is no recoil of the magnetic inhomogeneities, then one can use the principle of detailed balance. And that gives us that psi P minus delta P is equal to psi P minus delta P delta P. So this is another idea that you should use. One then Taylor expands this, and the expansion gives us, leaves us with this equality that, I mean, you take for granted now, but I want to just put some steps to arrive at the end of this equation in the same form I have written here. So the Taylor expansion on this other part leaves us with this equality that delta, the derivation over P of delta P over dt minus 1/2 d over dt delta P over dt is equal to 0. So we have this condition that I call 1. And we have the second, the right-hand side term, the right-hand side part of this equation, which I call 2, everything here. So we have the Fokker-Planck equation, which is our baseline, and using the principle of detailed balance, you can rewrite this first part as the second one and put it here. Okay, so this is I mean, from now on, it is a simple algebra. So you put 1 into 2. If you put 1 into 2, the Fokker-Planck equation, the term which is energy dependent, turns out to be pretty simple and to be the derivative over p 1/2 delta p divided by 2 averaged df over dp. So these are the steps that one must follow to arrive to this form for the energy change, the equation that regulates the energy changing. And one starts from the Fokker-Planck equation. So, since I still have some comments, but I mean, I didn't do any break, maybe I stop here, I recall tomorrow you this equation, and we go on with that.